Hi viewers, I am Dr. Ishwar Rao, lecturer in mathematics, JDC Cover. This is my first video lesson. My topic is groups. This is very important topic in algebra. Before going to discuss a group, we discuss the definition binary operation. Entire this video, capital G is a non-empty set. Binary operation is nothing but a function which is defined from G cross G to G. There is another remark for binary operation. A circle is said to be binary operation on G if and only if for any two elements A comma B, A circle B is also an element of G, then circle is called binary operation. And next, we discuss another definition, algebraic structure. Algebraic structure is nothing but a non-empty set contains one or more than one binary operations. Then that non-empty set is called algebraic structure. For example, real number set contains addition and multiplications are binary operations. So, real number set or comma plus comma dot is an algebraic structure. Now we discuss the definition of a group. G is a non-empty set. Circle is a binary operation. G comma circle is said to be a group if satisfies the following axioms, which is nothing but the following axioms are only four axioms. That four are, first one is closure axiom. Closure axiom is for every two elements A comma B in G, then A circle B is also an element of G. That property is called closure property. Associative property. For every three elements A comma B comma C in G, A circle B circle C equal to A circle B circle C. This property is called associative property. And third one is identity property. For every element in G, there exists an element E in G such that A circle E is equal to E circle A equal to A. Here E is called identity element. The property is called identity property. And fourth one is inverse property. For every element A belongs to G, there exists another element A inverse is also in G such that A circle A inverse equal to A inverse circle A equal to E. Here E is the identity element, A inverse is the inverse element of A. This property is called inverse property. G and circle satisfies the four properties, then G comma circle is called group. Next definition is abelian group. Abelian group means G comma circle is a group and then it satisfies another property which is called commutative property, nothing but A circle B equal to B circle A. For every A comma B belongs to G, then the group is called commutative group or abelian group. Abelian group means group satisfies another property. That property is commutative property. For example, Z comma plus is abelian group. Q comma plus, like that. These are all the abelian or commutative groups. This is an example for non-commutative group. The quaternion group is non-commutative group. G equal to set of plus or minus 1, plus or minus I, plus or minus j, plus or minus k, defined like this. Here operation is I square equal to j square equal to k square is equal to minus 1 and I into j minus j into k equal to k, k into I equal to minus I into k equal to j, j into k equal to minus k into j is equal to I. This is the operation defined like this. Then it is non-commutative because I into j is equal to k, j into I is equal to minus k. So commutative property not satisfies here. So it is only group, it is not commutative group. And then we discuss some theorems on groups. The first one is uniqueness of identity. In a group, the identity element is always unique. Proof. For proving this statement, the statement is identity element is always unique. So we have to prove that the identity element is unique. For that, suppose we take there are two identity elements in group that are E and E dash. Now we take E is the identity, then E into E dash. Here E dash is any element in G. We take here E is the identity element. E into E dash is equal to E dash into E equal to E dash. And next, let us take E dash is an identity element. Then use the identity property. E is the element, E dash is the identity. E into E dash equal to E dash into E equal to E. These two statements by using the identity property. Then from these two statements, E equal to E dash into E equal to E into E dash equal to E dash. So finally, E equal to E dash. Here we assume there are two identities in G, but finally we prove that the two identities are same, that is E equal to E dash. So for this proving, the identity element is always unique. Next, uniqueness of inverse. This is another theorem. This is uniqueness of inverse. In the previous theorem, we discussed the uniqueness of identity element. In this theorem, we discuss the uniqueness of inverse element. The inverse of each element of a group is unique. This is the statement. In a group G, inverse element is unique. We prove here for every element in G, its inverse element is unique. The proving is as usual what we discussed in the previous theorem, same proving we are use here. If possible, there are take two inverses of an element A, that is A and B. Suppose B is the inverse of A, then BA is equal to AB is equal to E. Suppose another inverse C. C is the inverse of A, then CA is equal to AC is equal to E. Here E is the identity element in G. Because already G is a group, E is the identity. From equation number 1 and 2, BA is equal to E equal to CA. Then BA is equal to CA. By using the right cancellation law, B is equal to C. Initially, we take two inverses of an element A, which are B and C. Finally, we prove the two inverses are equal. So inverse of any element is unique. Next theorem is the cancellation laws. First, what is cancellation laws? Cancellation laws is two cancellation laws are there. One is left cancellation law, other one is right cancellation law. Left cancellation law is AB equal to AC, then B is equal to C. This is the left cancellation law. BA equal to CA, then B equal to C. This is right cancellation law. Now our theorem is in a group holds cancellation law. That means in group cancellation laws are satisfied. Now proof is E is the identity element in G. Let us take A, B, C are three arbitrary elements in G. We prove that for left cancellation law, take AB equal to AC. Already G is a group, there is an inverse element in G. A is an element, A inverse also element in that group. So AB is equal to AC, multiply A inverse by left side. By using the associative property, A inverse into A into B equal to A inverse A into C. By using the inverse property, A inverse into A is E. So EB is equal to EC. By using identity property, EB is equal to B, EC is equal to C. Now we have taken here AB is equal to AC and then it comes B is equal to C. This is the left cancellation law. Next we prove that right cancellation law, BA is equal to CA and multiply A inverse from the right side. BA into A inverse is equal to CA into A inverse. Then using associative property, B into AA inverse equal to C into AA inverse. By using inverse property, AA inverse is E. So BE is equal to CE. Again using the identity property, B is equal to C. We take BA is equal to CA, then finally B is equal to C. This is right cancellation law. So in a group G, left cancellation law and right cancellation law holds. And next theorem is the left identity is also the right identity. That means identity element, left identity element is same as right identity element. Now proof. Let E be the identity element in a group G and A be the arbitrary element. E be the left identity, so EA is equal to A. We prove that this left identity is right identity. For that we prove AE is equal to A. This is the right identity property. Suppose A inverse is the left inverse of A, then A inverse into A is equal to E. By using the associative property law, A inverse into AE, we take associative property law here, A inverse into A into E. By using inverse property, left inverse property, A inverse into A is E. So E into E is E. Finally, that is E. Again using the left inverse property, E can be written as A inverse into A. Here A inverse into AE is equal to A inverse into A. Here left cancellation law use here, then AE is equal to E. This is the property for that right identity. So every left identity is same as right identity. And then next theorem is inverse rule. In a group G, A comma B are two elements, then AB whole inverse equal to B inverse A inverse. Proof is here our statement is AB whole inverse equal to B inverse A inverse. In the statement we have all inverses. So for the proving of this theorem, finally we use the inverse property. Consider arbitrary elements A and B in a group G, and A inverse and B inverse are the inverses elements of the respectively A and B. Then B inverse into B are B inverse equal to E, A into A inverse equal to A inverse into A equal to E. Let us take this as equation number 1. And then our statement is AB whole inverse. Here AB is an element, its inverse element is B inverse A inverse. So we take AB into B inverse A inverse. using the associative property A into BB inverse A inverse. BB inverse is E, so A into EA inverse. EA inverse is A inverse, so A inverse. AA inverse is E. So AB into B inverse A inverse is equal to E. By using the inverse property, AB whole inverse is equal to B inverse A inverse. This is generalize this result. Finally, we get A, B, C and so on whole inverse is and so on C inverse, B inverse, A inverse. This is inverse reverse rule. Next term is in a group G, AB an element of G, A inverse whole inverse is equal to A. Here A inverse is inverse of A. Proof. A inverse is the inverse element of A in a group G, then A inverse into A is equal to E. We prove the inverse of A inverse is A. Pre-multiplying by A inverse whole inverse, then A inverse whole inverse into A inverse into A is equal to A inverse whole inverse into E, because this is by using the associative law, A inverse into A is E. Then in bracket A inverse whole inverse EA is equal to A inverse whole inverse. EA is A. So A is equal to A inverse whole inverse. So in a group G, A inverse whole inverse is A. This is also another important theorem. Thank you. Thank you for listening very carefully my topic. Thank you.